This is video number 3 in the chemistry series, and our learning objectives are these for this video. Which two subatomic particles make up the atomic mass of an atom? And actually, I think you already know this answer based on the previous information you have covered. Number 2, what is an isotope? And number 3, all atoms are electrically what? Positive, negative, or neutral? Now, we can answer these very simply, but I do want to talk them through. So let me just answer them first. The two subatomic particles that make up the atomic mass are the proton and neutron. What is an isotope? It's a structural variation of an element with a differing number of neutrons. So the answer is neutrons. And all atoms are electrically neutral. Okay, so there's your answers to the learning objectives, but let's go and talk about them. Okay, so when you look at the mass, remember that one of the first things that you had to do with these atoms was you had to know what they are, the charge, and how much they quote weigh, or what the mass is. And I told you that protons have a mass of 1 AMU, neutrons have a mass of 1 AMU, and electrons have no mass whatsoever. And so protons and neutrons, as you know, live inside the nucleus, and so that's where all the mass is located. Everything out here in these orbits, there is no mass associated with the electrons there. So knowing that, then the mass number, is the number of protons plus the number of neutrons. So oftentimes we'll see elements depicted this way. It'll have a letter, and that letter here represents the name of it. And in this case, C stands for carbon. That's one of the big 4 that we care about. And then oftentimes you'll see 2 numbers. You'll see this number 12 and then a smaller number here, 6. Now, depending on the way these elements are depicted, I don't want you to think that the larger number is always on top and the smaller number on the bottom. So first of all, the smaller number is what you already know, and that is the atomic number. The atomic number is the number of protons. So what is the bigger number? The bigger number is the mass number, or the AMU, the atomic mass number, and that is the number of protons plus the number of neutrons. So you'll see here, this is 12, this is 6. So what does 6 tell you? 6 tells you the number of protons. What does 6 not tell you? It does not tell you the number of electrons. It does not tell you the number of neutrons. It tells you what? It tells you only the number of protons. So what does the mass number tell you? It tells you the mass. So, well, if you know that the mass is only made up of protons and neutrons, and you know that the number of protons is 6, then you can figure out the number of neutrons, right? It's 12 minus 6, which then equals 6. Now that might seem very easy to you, but let's do something like this. So ignore isotopes just for a second. I'm going to use this slide to talk about isotopes, but let's look at this. There are these weird flavors of carbon, which it's still carbon because it's got 6 protons. If you've got 6 protons, you're going to be carbon. But in this case, the atomic number is 14. So the atomic number is 14, and the atomic mass is 14. The atomic number is 6. Sorry about that. One more time. The atomic number is 6. The atomic mass is 14. So the atomic mass is 14. What are the things that make up atomic mass? It's number of protons and number of neutrons. So then from here, could you calculate the number of neutrons? Well, if this is the number of protons and neutrons, and this is the number of protons, then you subtract 6 from 14 to get the number of neutrons, which would be 8. So in this situation right over here, how many neutrons do we have? We have 8 neutrons. Now, going back to what I said, look, right now, the bigger number is depicted on top, the smaller number at the bottom, and it's not always that way. But here, let's memorize this. Carbon, atomic number is 6, mass number is 12. And what I want to do is look back at the periodic table. And we look at the periodic table, then carbon, the atomic number is 6, the atomic mass is 12. Here you're seeing the atomic number put on top and the mass number at the bottom. So there's no hard and fast rule for that particular type of thing, but the mass number will always be greater than the atomic number because it's always going to include the number of neutrons as well too. And you'll see that throughout. If you look at something over here, let's take something like hydrogen. Let's look at hydrogen. When you look at hydrogen, what's the atomic number? The atomic number is 1. There it is. The atomic number was 1. So that tells you hydrogen has 1 proton. What is the mass number? Well, it goes out to 3 decimal points, but if we round that, what's the mass number? It's 1. So then, can you calculate the number of neutrons that are typically present in a hydrogen atom? Well, 1 minus 1 is 0. So the answer is 0 neutrons. So hydrogen atom typically doesn't have any neutrons associated with him. You've seen that before. I didn't make a big deal out of it, but you've seen that in this slide. I showed you hydrogen. Hydrogen has 1 proton, and that's what makes him hydrogen. He happens to have 1 electron, which we'll get to later, but he actually has no neutrons inside. And that's it. Everybody else is going to have neutrons, but hydrogen is going to be that one exception. Okay? So now we've looked at, again, the mass number and the atomic number. Again, the unit is AMUs or Daltons, either ones you can use for mass number. So you know what atomic number is, you know what mass number is. Now then, let's go to the next learning objectives. So we covered this one. The next learning objective is, what is an isotope? Well, by definition, an isotope is a structural variation of an element with a different number of neutrons. So going back to the slide that I showed you, this is an isotope of carbon. He is still carbon. Why is he still carbon? He's still carbon because, and I know I'm a broken record here, but hopefully me being a broken record means you'll never forget this stuff. The reason he's still carbon is that the number 6, he's still got 6 protons. And as long as you got 6 protons, you're still carbon. Look, if you got 6 protons and 18,000 neutrons, which is a fantasy world, but if just pretend, in our fantasy world, if you had 6 protons but 18,000 neutrons, you're still carbon because of the fact that you got 6 protons. What if we changed it? What if you only had 5 protons? Well, if you only had 5 protons, remember, you are now no longer carbon. Your fundamental identity has changed, and you are now boron, this number 5 over here, okay? So let's go back to isotopes. Isotopes, again, are a little bit weird, I think, and different to think about. But again, I just need you to see that, look, if you had a bag full of, let me skip that for a second. Let me do this. If you go out there, I've got clovers all over my yard. There's very little grass, but a whole bunch of clovers. And so generally speaking, if you were just to blindly reach down and scoop up a handful of clover, they're all going to look like this. Most of them are going to have 3 leaves, unless, something's been torn off or something. But most intrinsically will have 3 leaves. Every now and again, though, every blue moon, you might find a 4-leaf clover. So is it still a clover? Yes, it's still a clover because its core identity, which is made up of, let me leave the metaphor for a second. It's still got the same number of protons. This guy still has the same number of protons as him. So the core identity is no different, that's for sure. But then, he looks a little bit different. So we basically call this a variation of this guy. But they're still clovers. They're easily and readily identified as clovers, but he is just a variation of this guy. So this is our 4-leaf clover. This is an isotope. This is an isotope. It's a structural variation with a different number of neutrons. One more time, it is a structural variation of an element with a different number of neutrons. So here are some isotopes of hydrogen. This is hydrogen because he's got 1 proton. If you look at this, he actually has 1 proton and 1 neutron. He's still hydrogen. I know the name says deuterium, but deuterium is just the name of the isotope. He's actually still hydrogen, so that's why this H is still there. Why is he still hydrogen? Because he's got 1 proton. But why is he a variation? Why is he considered a variation? Well, it's because he now has 1 neutron. You actually also have another rare isotope. This would be like a 5-leaf clover, which you're just not going to see except for every really rare blue moon. In that case, you'd still have 1 proton, which makes you hydrogen, but now you have 2 neutrons. Now look, I don't need you guys to memorize, what is the formula for deuterium versus what is the formula for tritium. I don't even need you to know these words necessarily, deuterium and tritium. I just need you to understand this theme of isotopes. So should we in A&P really care very much about isotopes? Truth be told, for the stuff that we do in normal physiology, we don't need to care about isotopes at all. Where you need to care is that some of these isotopes are radioactive, and different doctors and clinicians or researchers use the radioactivity of different isotopes to measure pretty important things in the body. So there are clinical applications to these things, but for normal healthy physiology, we don't need to concern ourselves with isotopes. Now, let me come back to this theme here, 3 and 4 leaf clovers. So now I reach down and I grab a handful of clover, and let's say I've got 100 in there. If I've got 100 in there, then maybe 99 of them are 3 leaf clovers and 1 of them is a 4 leaf clover. Okay, let me change that. Now I'm going to reach down in somebody else's yard and maybe let's stick with my yard, and I grab, another 100 clovers. And so maybe 99 of them, let me take that back. Maybe all of them are 3-leaf clovers. I do it again, all of them are 3-leaf clovers. I grab another 100, all are 3-leaf clovers. Throw them down, grab another clump, they're all 3-leaf clovers. I do it again, and I reach down, and now, wow, I just found a 5-leaf clover. Okay, so now that was 1 out of 900 or something like that, right? Here's why that's important. I'm just going to make up some numbers here. Let's say 1 out of every 100 is a 4-leaf clover, 1 out of every 1,000 is a 5-leaf clover, and that's really it. We don't really observe 6-leaf clovers ever in nature, okay? if you're following my analogy. So here's why that's important. The reason that's important is because of this periodic table. See this mass here? It says 1.008. The question might have come up like, what has a mass of 0.008? If a proton has a mass of 1 and a neutron has a mass of 1, how are you getting this weird number like 1.008? Well, and you'll see that continuously. Look at carbon, it's 12.01 is the mass. Nitrogen, 14.01. Magnesium, 24.31. So where are we getting these weird decimal points, these fractions of units? How is that actually happening? Because protons have a mass of 1, neutrons have a mass of 1. Well, here's how it happens. Out there in the world, scientists have determined that out of all the hydrogens out there, that's most of it. I'm just going to make up numbers here. I don't actually know what they are, and you don't need to know what they are, so let me just make up numbers to make a point. The vast majority of them, like 99.5% of them, are hydrogen that looks like this, and then 0.04% of them are hydrogens that look like this, and then 0.01% are hydrogens that look like that. So that is all the hydrogen out there in the natural world that we can observe. Well, so what scientists have done then is that they've added all those things up to determine an average atomic mass, given all the variations in isotopes. And when you take an average out there, that's when you get 1.008. Okay, so that's not like an important factoid that's testable and things like that, but it hopefully demystifies these fractional atomic mass units. So the ones that we care about, carbon, it's an atomic mass of 12. I'm just going to say it's an atomic mass of 12. We don't need to memorize 12.01. But I want you to be able to make that make sense, so you're not thinking to yourself that, oh, geez, did I lose just a segment of my neutron? Did I just shave off just a wee bit of my proton? That's not what happens. It's because, again, out of all the carbons out there in the world, most of them have 6 neutrons. Some of them have 7 neutrons. And maybe you got some with 8 neutrons out there. And then when you kind of get the relative proportion of those and average them out, you get 12.01. Okay? So that's really it when it comes to understanding the atomic mass and isotopes. Oops, that's the wrong slide. Let me jump back to where we're at. All right, so where are we? Which two subatomic particles make up the atomic mass? You know that now, protons and neutrons. Isotopes are structural variations of an element with a different number of neutrons. And then all atoms are what? Now, this is really important. This is really important. All atoms are, and I'm gonna qualify this. All atoms off the factory line before chemistry happens are electrically neutral. Okay, all atoms before chemistry happens, before they start interacting with their environment and things like that, are by design electrically neutral. So what does that mean? Look, protons are positive and electrons are negative. Neutrons have no charge whatsoever. So therefore, we can conclude that in an atom, a fresh atom off the factory line, so to speak, the number of protons is the same as the number of electrons. So the number of protons is precisely balanced by its number of electrons. Again, this is before chemistry. Keep in mind, if atom number 1 and atom number 2 are going to talk to each other and do some chemistry, they're going to negotiate electrons, and they may give away or pick up or share, and they're going to barter with electrons. But before all that stuff happens, atoms are electrically neutral. So what does that tell you? It tells you something like this. When you look at that periodic table, carbon, what do these numbers tell you? The atomic number tells you that carbon has 6 protons. The atomic mass tells you that, well, it has a mass of 12, which is made up of protons and neutrons. So if I subtract the atomic number, I get the number of neutrons. So based on this, I can calculate the number of neutrons as also being 6. But what else do you know? Carbon has 6 electrons. That's what you know as well, too. Carbon has 6 electrons. Because if it's got 6 protons, and the rule is that these atoms are going to be electrically neutral, then you got to have 6 electrons as well, too. What about oxygen? How many electrons does he have? He has 8. How about nitrogen? How many electrons does he have? He has 7. Now, I don't blame you if you were to say, whoa. Are you telling me then the atomic number is the number of protons and it's the number of electrons? And I got to stop you. No, we can't say that. The atomic number represents only the number of protons. That's it. Because the number of electrons can vary down the road. But what the atomic number represents by definition is the number of protons. We can also say However, the number of protons off the factory line is equal to the number of electrons in an electrically neutral atom. So therefore, you can figure out how many electrons you have before chemistry happens. All of that, I recognize, still might sound a little bit, dude, you keep saying before chemistry happens. I don't know what you're talking about. What do you mean? What do you mean by negotiation of electrons? I don't blame you if you think that, and I will get to it, but I got to establish these ground rules first before we get into those things. So just to recap, this is our recap slide. We've covered all these learning objectives, and hopefully everything's been clear to you. What I will tell you is that number 2 is kind of like a simple definition, maybe one question on your exam that you need to know. But this number 1 is really important for your foundational understanding of an atom, and number 3 is really our starting point for understanding how an atom works and whether or not it wants to do chemistry with other atoms. So number 3 becomes very, very important in future videos.